Okay, everybody, thank you so much for joining us. Let's go ahead and get started. I believe everyone can see my webcam, and you should be able to hear my voice. We've got all attendees muted just so that we can limit the background noise, but if there is any problems, please feel free to enter something into the chat box of your webinar toolbar, and you will also see in that webinar toolbar that there is a handout. There's a handout there that you can download. It's the case study for the information that we're going to be presenting here today. So without further ado, let's go ahead and get started. I'm really excited to share this case study with you guys. Again, excuse me, my name is Trollier, and I'm with ECO2. I'm going to be presenting a case study that we did last year. This is a project that was completed last year, rather, at the city of Grand Rapids, Minnesota. And this is a plant that is discharging to the public wastewater treatment plant. I'm going to tell you a little bit about what their problems were and what they did to resolve those problems and some of the economics and some results as well. So up in Grand Rapids, Minnesota, I put a little map there, and you can see that it is right near the headworks of the Mississippi River. It's kind of fun to just take a look at where different plants are along different waterways, and this one is up at the top, and they've got this beautiful, cold, clean water, and of course the industries around there are able to use that water for cooling. And the one that we're going to look at today is no different, and this is a paper mill that's been in Grand Rapids since 1901. It's now owned by UPM, so it's called the UPM Blandin Paper Mill. And so what they're doing is they're making a whole bunch of paper. It's a real high-capacity plant. And the wastewater that is produced from that plant and that process is pumped about a little over 2 miles to this wastewater treatment plant that you can see right here. So that's operated by the Grand Rapids Public Utilities Commission. But the problem is that this plant was having a lot of odor problems. You can see that they've got the primary clarifier, and then they've got a kind of a conventional plant. You wouldn't think that that would have too much odors, but they're receiving a very large portion of their flow from the paper mill, and it's pumped through a 2-mile force main before it gets to the plant, and then it goes through a primary clarifier, which is also void of oxygen. And so that's where the odors were coming from, both the force main from the paper mill to the plant and within the primary clarifier at that public works treatment plant. So the treatment plant handles about 4.3 MGD, million gallons per day, and 70% of that approximately is the plant, the paper mill industrial wastewater flow. So a lot of what happens at this Grand Rapids plant depends on what they're getting from UPM. Now, the paper mill also has very changing water quality characteristics, as well as high loads, varying flows. So it's a little bit of a challenge treating that wastewater. Excuse me. Sorry about that, everybody. Okay, so as I talked about in a primary clarifier, you may not think that this is a large odor source, or maybe you work at a plant and you've got covers on yours and scrubbers and you're very familiar with H2S, but really what's happening inside this primary clarifier is similar to what's happening inside of a force main. When there's no chance for air or oxygen to get to these lower depths, you've got an anaerobic or an anoxic environment, and under those conditions, H2S is formed. The bacteria under anaerobic conditions create H2S. Bacteria do not create H2S under aerobic conditions. So what happens here is you're getting the dissolved sulfides formed here down inside the clarifier, and as that water rises to go over the weir in the effluent, that dissolved sulfide comes into contact with the air and is liberated as H2S gas. So you can get very high odors from the effluent weir of the primary clarifiers. So here we are taking a look at the map of the city of Grand Rapids, Minnesota. So we've got the plant over here in the bottom right corner, and the paper mill is all the way up here, also along the river. But like I said, a little over 2 miles that this wastewater has to travel through an isolated force main. So there's not a lot of other contributions coming into this line. And this is what made it really ideal for oxygenation. So we could treat up at the very beginning, right at the paper mill, and we can establish those aerobic conditions throughout the length of that force main so that when that wastewater arrives at the treatment plant, it has a positive DO, and that positive DO continues through the primary clarifier, removing sulfides throughout that entire process. Now that's what we're going to talk about what the solution was. But before they came up with that solution, the city of Grand Rapids had looked at several different options, multiple different chemical feed options, and the most success they had was with the calcium nitrate liquid chemical feed. And to do the best job they could with that, they were still getting odors. And the cost to use that calcium nitrate was almost $500,000 a year. They just had to feed so much of it to try and knock down those odors. So in search of a better solution, they reached out to another facility that had a similar problem, which was a UPM paper mill plant up in Maine. They had done a similar project back in 2012. So I'm going to show you what they found when they went up to Maine and they took a look at that other plant. So this other plant is up in northern Maine. It's in Madison, Maine. It's operated by Woodard and Curran. And now this plant no longer does take paper mill wastewater because their paper mill closed. However, 10, 12 years ago, this is what their H2S looked like before they started treating with oxygen. So they had really high levels at the primary clarifier effluent weir, just like at Grand Rapids. And they didn't have a long force main, though, leading to it. The plant was fairly close to the paper mill, so they had frequent odor complaints from that wastewater treatment plant. They had high H2S, and again, their chemical solution was cost prohibitive. Up in Maine, it was about $320,000 per year to treat with the calcium nitrate and still not get perfect results. The odor was reduced, but it just was not eliminated. So what they decided to do was they installed this superoxygenation system. It injects high purity oxygen. It's maybe around between 90 and 100% pure oxygen. And this is a process we call superoxygenation. It uses the Speece Cone. It's a side stream process, so it takes some of the flow that's going into the clarifier and it passes it through the Speece Cone where it picks up the high level of dissolved oxygen and it goes right into that clarifier. Now, it's important to note that the settling is not affected in the primary clarifier or hydraulic conditions are not altered in any way, simply because we are just adding dissolved oxygen. We're not adding any air, and we're not just diffusing oxygen bubbles. We're actually transferring all of that oxygen into the liquid within that Speece Cone. I'll show you a little bit more about that in a minute. But this is what the project looked like. I've got a little sample drawing here of the Maine project. So this is their clarifier right here. And you can see they've got their side stream going through the Speece Cone where it's getting the oxygen, dissolving it, and going right back up into the influent chamber of the primary clarifier. And the intent, again, is to keep this liquid aerobic so that when it comes over the weir, there's no H2S. So they installed this back in 2012. Got a couple of more photographs here just to show what this thing looks like. The pumps that are in this little pump room right here, you can see they've got a duty standby. Those are pushing liquid through this cone, and we're getting a dissolved oxygen reading on the DO meter right at the effluent of this cone of 62 milligrams per liter. Now you may be thinking to yourself, gosh, that sounds like supersaturation. Really, it's not. It's staying below the saturation level is key in these superoxygenation projects. Now, it's important to note that the saturation level is different with air than it is with pure oxygen. The saturation level with no pressure on water with air is about 8 to 9 parts per million. It's 5 times that using pure oxygen as the oxygen source. So with zero pressure on the water, you can easily dissolve up to 40 milligrams per liter of dissolved oxygen using this Speece Cone process. Whenever there is additional head, whether it's from height of the water or pressure in a force main, the level of oxygen that you can dissolve and stay under saturation continues to increase with more pressure. It's Henry's law, and it's really not doing anything magic. It's just using those laws of science that are very well established. Now, the folks at Grand Rapids were a little skeptical, and they said, are you sure that in the clarifier you can achieve a DO residual coming out the back end of it, and it's not going to interrupt your settling? And they said, yep, take a look at this data. Here we've got an H2S logger on the grate at the effluent weir of the primary clarifier, and a DO probe going down into that effluent weir channel. So here you can see there's 0 H2S on the logger, and there's a DO residual of 12.42 coming over that weir. So the odors were eliminated. Oops, pardon me. The odors were eliminated. They were saving a ton of money. The capital expense at this location was about $800,000. The annual O&M, as opposed to $320,000 for chemicals, was only $20,000 for everything here. The oxygen supply, the pump to run the side stream, all the operating costs for the ECO2 system were just $20,000 a year. So their return on investment for chemical payback was about 2.4 years, and none of the settling processes were interrupted. So the city of Grand Rapids said, okay, well, that sounds like a pretty good deal. Let's go do that. So this is, there were probably a lot of conversations that I was not privy to as far as the partnership between the paper mill and the city of Grand Rapids. But what they did here was they said, all right, we're going to install this and inject oxygen at the beginning of that force main before it pumps all the way across town. And we're going to put enough dissolved oxygen in there to satisfy the bacteria throughout that entire pipe run and the residual or the retention time of the primary clarifier. So here's some of those details. We had quite a bit of pressure in that force main, 83 feet of static head, 86 feet of dynamic head. The retention time of the force main is about 2.5 hours. And there was another about 2.5 hours of retention time in the primary clarifier. So we wanted to have a dissolved oxygen carryover when it hits the plant. So we had a total dose at the very upstream portion of 60 milligrams per liter in order to last all the way through that clarifier and have a positive residual coming out the back. The system has a 6-foot Speece Cone driven by a 25-horse side stream pump. There are controls so that all of the oxygen feed is automated based on force main flow and times a year and different things like that. Also included in the project were the oxygen tank that you can see here. I call it a LOX tank. LOX stands for liquid oxygen. So this is cryogenic liquid oxygen that a truck pulls up to about once a month, and they offload it, fill it in there, and then it runs through this vaporizer to become a gas again. And then we dissolve it in the cone, and the dissolved liquid oxygen goes right back into the force main. So altogether, their price on this was about $455,000 all installed. They did the engineering in-house. Now I want to tell you, you might be thinking, what's a Speece Cone? Well, if you take a look inside that thing, here, this one has a gentleman sitting inside of it, and he's welding. And I like to show this photograph just because it illustrates that there are no baffles, nozzles. There's nothing inside the cone. It's hollow, and there's nothing there to get plugged or reduce flow or require maintenance. When Dr. Speece invented this, he called it the downflow bubble contactor, but it's become known as the Speece Cone, and it is patented, and ECO2 is the only provider of the Speece Cone. They come from, we make them in very varying sizes, from small, which would handle maybe a half an MGD, up to extremely large, maybe 10 MGD flowing through a single cone. Oops, sorry about that. So I wanted to just show a little bit more about that Speece Cone process and what it looks like, because at the pump station you can't see much there, especially when it's covered in snow. So really what the Speece Cone is it's just a method to quickly and completely dissolve a pure gas into a dirty liquid water stream or tank. Here is Dr. Speece next to one of the cones, and here's a cutaway view of what this process looks like, very much at Grand Rapids. They've got that paper mill industrial pump station, and it is pumping down to the city. And we have tapped into that pipe twice. So we're taking a side stream off of that force main, pumping it just a little bit to overcome losses. It goes through the cone where it picks up the oxygen, gets dissolved, comes back out and back into the force main, and then continues on to the treatment plant. Taking a look inside that cone, just a graphic here, it shows kind of how this thing works. You got the oxygen gas just being piped into the side near the top of the cone. And as the water comes in the top, it's moving at a really high velocity, and it smashes the bubbles into a really turbulent zone, and then it gets laminar again as it's moving out the bottom of the cone, and the velocity of the water leaving is lower than the buoyancy velocity of the small bubbles. And so it's just the hydraulics and the geometry in this cone that retain the bubbles inside, and the only way for oxygen to get out is to be dissolved. It has very high oxygen transfer efficiency, as proved in over 100 installations now. Now, just to show you a little bit about the results there at Grand Rapids after they did the installation, they've got a positive DO from plant to plant. So at the beginning of the force main, they're putting 60 milligrams per liter of oxygen in, and it's all staying dissolved throughout the process. At the primary clarifier influent, they're getting about 20 milligrams per liter on average. This is a chart of those readings taken throughout several months. And then at the primary clarifier effluent weir, they've also got a positive DO level. And this allows them to have 0 H2S at all those locations. I put a few more shots of the DO meter as we were starting this up and doing the performance testing at that paper mill pump station. So this is showing the DO going into that force main at the beginning. Now, the economics of this case study were pretty impressive. The maximum capacity of this system is 2,000 pounds per day, if you're keeping track. So it was about 4 MGD, about 60 milligrams per liter, 8.34, comes out to about 2,000 pounds per day was the maximum capacity that the system was designed for. Now, with lower flows or lower needs, they can taper that feed rate down. They don't have to feed a constant 2,000 pounds, but that's what the system maximum capacity was designed for. Now, the cost to operate this, including the liquid oxygen tank, the lease, the supply of the oxygen gas, the cost to pump this liquid through here, and for all maintenance is just over $26,000 a year, as compared to the $500,000 per year for the chemical calcium nitrate alternative, which wasn't having the desired impact. So with oxygen, they were completely eliminating the odors and the corrosion and the safety hazards, and saving almost a little over $400,000 per year. So with the capital outlay, 381 plus 75K installation, their return on investment just on the chemical payback was less than 1 year. So you may be thinking to yourself, with economics like that, and if the results are so much better with oxygen, why doesn't everyone use oxygen anywhere there's H2S? Well, first of all, superoxygenation is really ideal as an upstream treatment. So the sulfide forms in a typical force main where the oxygen has been depleted because it's an enclosed pipe and it's flowing a long distance, and there's no chance for air to get into that pipe and re-aerate the liquid. So anytime the dissolved oxygen reaches 0, you've got a formation starting of dissolved sulfides. And then when that liquid hits the air, it comes into contact with air, the H2S gas is released, and that's where you get the major odor problems and corrosion and safety issues. Now, don't forget about primary clarifiers, because this can be a very large anaerobic environment, and without chemical treatment, you can get really high H2S coming over those effluent weirs. Many municipalities and treatment plants will elect to put a cover on these and then install a vapor scrubber. And although that is a very good way to control odors, you still have high levels of corrosion going on in there, and those are very expensive options to install and maintain. So this may be a good application for superoxygenation, as well as force mains that have a long travel time and are allowed to go completely anaerobic. Because keep in mind that sewer in a collection line or in a tank, when it runs out of oxygen and it doesn't have any nitrate, the bacteria will reduce sulfate to sulfide. Now, if you give it oxygen or nitrate, it will oxidize that back to sulfate. And just to kind of reiterate that the bacteria are really not respirating, but they're looking for an electron acceptor, and their favorite thing, kind of like their favorite food, is oxygen, or their favorite thing to breathe rather might be oxygen. If oxygen's not there, they will use nitrate. So if you were feeding both, they would use the oxygen first, then the nitrate. When both runs out, then you would start to get the sulfide generation. So I'd just kind of like to wrap up here with a couple of things maybe you can carry on with you and think about whenever you come across hydrogen sulfide from a sewer collection system or in a plant. Just remember that sulfide is created when there's no oxygen. If you just want to give it what it needs, you can feed dissolved oxygen now because of the Speece Cone. And oxygen is very inexpensive, but without the Speece Cone, it's fairly difficult to dissolve because of its low solubility. With this process, we were able to get very consistent results. It's fully automated for the lowest operating cost possible and very minimal input from the operators. It doesn't interfere with the force main hydraulics or the clarifier settling process. It's good to remember that the only moving part is the side stream pump on this thing. And also, oxygen is really environmentally friendly. If you compare the carbon footprint to a chemical source, oxygen is dramatically less, has a dramatically lower carbon footprint. It's very inexpensive to purchase, and it's available in almost every city in the country. It's also used for medical, so it's pretty easy to get. It's just kind of hard to put it in the water, and that's what the Speece Cone is for. With that, I would like to open it up to any questions that have been posted, maybe in the questions section of the webinar toolbar, or if you've got maybe something to put into the chat. I see that there are a couple of questions here, so I'm going to take a minute and just read through those. I believe that you mentioned doesn't add air to the force main, correct? As it is correct. Yeah, so the question says, clarify that there's no air being added to the force main. Yeah, in superoxygenation, we're using only high purity oxygen gas. So if you were to take a look back at that system, you don't see an outlet anywhere. So without bubbles leaving the bottom of the cone, we are dissolving all gases. And so air is only 20% oxygen. So with aeration systems, that's why you have a lot of bubbles, because only the oxygen could really be dissolved. And so that's why we don't use air, and we don't compete against aeration applications, really. We're very good at applications that require just high levels of dissolved oxygen, but cannot tolerate bubbles or undissolved gases. Thank you very much for the question. Let me see if I've got any more. I do have a question here about force mains versus gravity mains. That's a really great question, and without going into a whole lot of detail, the answer is yes, you can use superoxygenation on a gravity line. you can dissolve up to 40 parts per million with zero pressure on the water. So say we've got a gravity channel going into a primary clarifier that, and we don't want to super saturate. We can put in 40 milligrams per liter, which would last potentially 4 hours of retention time based on the industrial averages for oxygen or for bacteria respiration rate or oxygen uptake rate. So if there are other applications that you'd like to investigate, I'd really encourage you to reach out to me directly. I've got my email here on the screen, my phone number, and also our website there. And also just don't forget to download that handout for the case study. And I think that's all the questions that we've got, but I really do appreciate everyone joining us today. And if there are any other questions, please feel free to reach out to me directly. And also let us know if you'd like a certificate of completion to use for CEU credits with your local chapter. All right, everybody. Thanks so much for joining us. Take care.